Welcome to this session on Ensemble Model. We'll be looking at random forest. So this is probably the most important topic that we should discuss. What we will understand here are a couple of algorithms that are the most preferred algorithms for predictive models in the industry. So let's start by understanding what is an ensemble. So ensemble in a simple language is a collection of models, right? So far we have looked at different models. We have looked at linear regression. We must have looked at logistic regression. We have looked at LDA. We have looked at decision trees. We have looked at KNN. We have looked at naive Bayes. So each of these models we have discussed previously work on individually, right? They have got different concepts under the hood, right? A linear regression model will have a linear equation, a logistic regression will have a sigmoid equation, so on and so forth, right? So what is an ensemble? It is if I combine all of these models into one and then use that model for prediction, that is known as an ensemble model. Today we'll be looking at ensemble model for random forest, right? So it can be a collection of similar models or collection of different or non-similar models. So what are we going to learn today is a collection of decision trees. That means if I combine multiple decision trees in one model, what kind of ensembles can I create? There are different ways of creating that ensemble. So bagging and boosting, these are the two ensemble techniques that we use on top of decision trees, right? The CART models, where the criteria of building the models was on the basis of gene impurity, where we split the load into binary outcome and then we continue to grow the tree till the time impurities were minimum, right? That's what we did. But with decision trees, we know that they are hungry models. They easily overfit. So if there is any kind of noise in the data, it will impact the overall decision tree. So what we did was we pruned the trees, right? We did some hyperparameters. We changed some hyperparameters, right? We defined some hyperparameters so that the trees don't overfit and give valid outcome. So bagging and boosting are the two ways in which I can combine multiple decision tree. So let's understand first the process of bagging. So let's say, for example, I have these 5 decision trees. This is my tree 1, this is my tree 2, this is my tree 3, this is my tree 4, this is my tree 5. I have a train data, right? Now, if I feed all of train data to each decision tree, will I get a different outcome from these trees? No, right? They will give me the same set of output. So, the algorithm that we use is bootstrap aggregation. What does bootstrap aggregation do? It will allow 68%, or it will deploy 68% of the observations at random to each of these decision trees, right? And we will get an output for the observations. So since this 68% of the train data is allotted randomly to each decision tree, I can expect a different output from each decision tree. Say for this decision tree, I got an output of 0. Here I got an output of 1. I got an output of 1. I got a 0 again. I got a 0 again. So what is the output? So for that observation, my 5 decision trees, after doing a bootstrap aggregation, they are giving me these outputs. I take a majority vote. So the majority vote here is 0. So my final prediction will be 0 for that observation after doing bootstrap aggregation. Under bootstrap aggregation, there is also something known as, we looked at bootstrap aggregation, right? So under bootstrap aggregation, there is also something known as randomly selecting the variables. That is known as random sampling, right? So what I can do here again, I can select, say if I have got 16 observations, 16 variables, right? I can select that I want to give at random 10 variables to each tree. So along with 68% random observations, it will allot 10 variables randomly to each tree. And again, each tree will give me some output, and my final prediction for that observation will be the majority vote. So this is what is bagging, right? Now let's look at boosting. Now this concept is also known as random forest. Okay, now let's look at what is boosting. Now for boosting, as in for when we looked at bagging, they were parallelly processing the data, right? 68% random observations, 10%, 10 variables randomly selected, given to the trees. Now, in boosting, what happens is, I've got these 5 decision trees. That's an example. It can be more. I've got these 5 decision trees. I've got this train set. In boosting all the train data, I do have a choice here if I want to give 100% train data or I want to give a sample. All this will be fed to tree number 1. After tree number 1 has processed, trained, it will give me prediction. Say it is giving me 85% accuracy and it has given me 15% errors. Now, sequential, the next sequence is the tree 2, which will concentrate on the errors. It will process the data again, but it will give more weightage to the errors. Say after tree 2 has processed, it has given me 83% of accuracy, so 87% of accuracy and 13% errors. So I do see an improvement here. 2% of my errors were taken care of. Same way, now T3 will again give more weightage to the errors and give its predictions. So this way, this will happen in a sequence. So this is what is known as boosting. So bagging is parallel processing and boosting is sequential processing, right? So this is how you differentiate between bagging and boosting in random forest. Thank you.